They sell to 20 people a day. 200 bucks a day.
And all they do is sit out there.
So what about cops?
No cops were there yesterday, amazingly.
Is there usually?
When I went last weekend,
Is there like a
the
hangout
same.
spot?
There's the same two
Or do
sheriffs.
you just drive by?
No, you drive and then you turn around and you ride back and you turn around and you ride back. Do little loopy loops up this certain part of the freaking highway. I'm serious. That's serious.
Where are you talking about?
She rides her
Riding.
motorcycle down the
On the
94 and they
94.
take pictures of her.
Who takes pictures?
Exactly. That's my question.
The photographers that sit out there around the corners.
Oh, and they just like taking pictures of people speeding by on their motorcycles?
No.
Websites.
You ever go up to Palomar?
Here, look, see?
Palomar
That
is
was me
scary.
yesterday.
Dude, alright.
And the guy was sitting there taking
Very
pictures,
nice.
and he
Then
puts
you go
it
to the website
on the
and buy a
website.
picture, basically.
But like that's just like a crazy.
I'm gonna have to make a problem about what angle could you go to before you wipe out. Oh yeah. I must go and destroy your mess up your bike with my map.
That's funny. So do people drive by in cars? Do they take pictures
Yeah.
of the cars too?
It depends on how nice the car is. Like if it's a vet or like an old time car, they'll definitely take pictures.
Alright guys, I want to show you something. Somebody came up and asked me about that root 3 over 2. And I had in my head a harder way to do it, and then as he's talking to me, I remembered, well actually I kind of created it and then remembered it's another way to do it. If I start with a equilateral triangle, so this is taking us back. How many degrees in each angle for an equilateral triangle? 60. It's got to be 60. It's got to be the same. They got to make 180, so it's got to be 60, 60, 60. So far, so good? Now, if I drop down the height, what did I just do to this angle here?
Cut it in half.
Cut it in half, so now it's 30 here. Let's make it a 1, 1, 1. Just because. And now look at that right triangle here. We draw that sucker. Let me turn that around here. How long is this? 1/2. So this is now 1/2 here, right? This is that 30 degrees from there. Is that cool? Because we cut that in half. And this is, of course, is the 60 from here. And this is the 90 from when I dropped this down. How are we doing so far? All right, so now how do you get that? And this is 1, of course, by definition. That's why that's 1/2. So if I were to define this to be 2, that would have been 1. All the ratios would still work out the same, right?
Yes.
Okay. So how do I get that side? Yeah. So this side would be 1 squared minus 1/2 squared square root. Just to cut to the chase. Just throw it in and see what you get. 1 minus 1/4 is 3/4. The square root of 3/4 is square root of 3 over 2. That's where the root 3 over 2 comes from. How we doing? So cosine of 30 must be root 3 over 2, because that's what the x side is. So 1 is the hypotenuse, so I won't change it. Is that cool?
Just do the sine of everyone. Like the sine of 30 and the sine of 60 and the sine of 90. You just get them all.
Well, yeah, sure. There you go. If you need to, just to let you know, and I want to apologize for, I'm sure if you looked at your homework sheet, we are going to bounce around between 5 and 6. Today we've basically been going forward 5 and then 6 and then 5 and then 6 and then 5 and then 6. It's just the way they set this book up. That's the one thing about this book I really hate. 5 and 6 should be one big chapter. Because radians are degrees. They're just an alternate way to measure. It's like you want to use inches or centimeters. Who cares? Oh. Well, it depends on if you're using a socket wrench, but let's not go there. On page 445. If this helps you for some reason, there's a table of values for angle measures and what sine and cosine and even tangent are. Page 445. Okay. It also has values for some trig functions we haven't talked about yet. We'll talk about them here in a little bit. Okay, just want to make sure I don't skip anything. Cool. All right. So just to fill in a couple holes real quick. If I have some angle, and I want to know how long this is. This length here is called the arc length. Going into calculus, remember that phrase, arc length. It kind of makes sense that the angle and the arc length should have a direct relationship. As one grows, the other one kind of grows at the same rate. You with me? In fact, we know it to a certain extent. Radians is a measure of arc length for the unit circle. So we want something more general. We want for any r, any radius there. So you can kind of do it with a specific example and then take a step back and see what you did. So here's a specific example. If I was at, if theta was 60 degrees and r is 10, let's say. Let me see if any of you guys can tease this out. And I'll give you one little clue. You have to know what this whole thing is. So kind of work back to see what this piece is. Yeah, so that whole thing, of course, is the circumference. If you leave things in terms of pi, don't put the value of pi in there. All right?
So it's pi r in the circle.
So what do you get for the circumference?
62.8.
So how many pi? Twice the radius? 20 pi. Cool. That's all the way around. So that would be, in terms of degrees, that would be 360 degrees. That's how much I get. So it's pretty simple. How much do I want then for just 60 degrees? Yeah, divided by 6. You with me? So if I want 60 degrees, I want whatever the ratio is of 360 divided by 60, that's how much I want of it. How much do I have to cut this down by? 1/6. With me? A little bit? So it'd have to be 1/6 of 25. Maybe. What's that?
Don't fit 25 over 6.
Yeah, okay, 25 over 6. And then, of course, that can reduce and all kind of business. So how do you do this more generally then? Say again?
20 times 180 over 6.
20 times 180.
Should translate to radians, or? Oh no, we already did that. No.
That's right, don't worry. So what we just did was this. We did 60 degrees out of 360. That's the 1/6 times the 2 pi r that we got, right? Isn't that how we got to where we are now?
Yeah.
Okay. Yes, sir.
1/6 because that's what you had before?
Because how much is 60 degrees of the whole circle? Wouldn't it be 1/6 of the whole circle?
Yeah.
It'd be 1/6 of a piece of pie, 6 pieces. You with me? Cool. All right. So I'm trying to work backwards to what the real formula is going to be.
Why not 25?
How do you
Yeah,
mean?
it is 25.
You have
3 pi over 6.
Yeah. In this case, 25. Yeah. My brain, I'm trying to work backwards to more general now. That's too specific. I want to know, what do I do always? Do I always have to do that? No. We take the angle that we're at, divided by 360, or even better in general, 2 pi. 2 pi times 2 pi r, and that'll be our arc length. And look what's really nice here.
They cancel.
Yeah. So as long as it's in radians, here's what's really nice. If it's in radians, the arc length is just theta times r.
So it's 60.
So let's try this again. 60 degrees is what in radians? What's 60 in terms of radians?
Pi over
What do you divide 180 by to make 60?
3.
I would agree.
3. So it's pi over 3. Let's try this formula out. So for this problem, it would be pi over 3 times the radius, which is 10. 10 pi over 3, isn't that what we got? When you reduce that bad boy? Right? So this is the general formula for arc length. As long as your angle is in radians. Good. So let me do this again. Why does that make sense? Degrees are made up. So if I have degrees times the radius, I get like degree inches, or whatever the radius is in. You with me? That doesn't make a damn bit of sense. Degrees is totally made up. Radians is truly a measure of length. It truly is. And in general, just to really, let me see if I can hammer this home. Radians sort of steps out of the way for other units. Radians is more of a, how can I say this? Radians is more of a ratio. So that it really didn't have any units. We kind of give it the units of radians just so I can feel more like I'm measuring around a circle. But it steps out of the way. So if radius here was in inches, my arc length will also be in inches, which makes more sense. Yeah, maybe. All right.
Can you measure it by like radians? Can you do it not inches like radians?
Can we do, I'm sorry?
Radians, not inches? Like
No,
there are.
no. Radians gets out of the way for other units. Radians, how can I explain this fully? Radians is sort of a lowest terms. So it's sort of like all the units have canceled out, but we still give it the term radians just so I can think about it in terms of the unit circle. Let's see, how can I do this more generally? So wouldn't, so for a unit circle, 30 degrees is pi over 6 radians, which means that's how far I've gone. With me? Cool? But if that's if the R is 1. If the R is 2, it's not pi over 6 anymore, is it? So pi over 6 is like lowest terms. I've done the ratio, so all the units have canceled. I still call it radians, so I can ascribe to it some kind of feel of unit of measurement. Just like degrees. What are degrees? They're completely made up. Radians aren't made up, but they are kind of unitless. We just call it radians so I know what I'm talking about. If I said 5 radians, you know I'm talking about going around a circle until I've gone 5 radians worth of movement. You with me? So they will get out of the way. So if I had 10 pi over 3 radians, inches, these go away, and then it's just inches.
No, when you what?
Second?
Like you cancel out.
They don't cancel. They're just not really there. It's because
It's an imaginary.
the unit circle itself is in lowest terms. I've kind of like reduced everything down. But we give it the term radians so that we all know what I'm talking about. If I said 7, if I say 7 radians, oh. If I say 7 degrees, oh. Those are totally different ideas, right? Which one's bigger, 7 degrees or 7 radians? Yeah, because how much is just halfway around? 7 degrees would be like right there, right? What's this? Isn't this pi? Isn't this like 3.14 radians? So 7 radians would be more than a full way around. 2 pi, 6.28, so 7 would be, so it's gone all the way around and then a little bit more. You guys kind of with me? Okay, good. A little bit, or at least you're just trying to make me feel better. You should still appreciate it. All right, so the main thing to get out of this is, here is the formula for arc length. Yes, sir?
Is the question asking in inches, or can it be like centimeters or feet?
It could even be in radians if they don't tell me what the R is. If they don't give me a unit, then it would be in radians.
Okay.
So just like for the unit circle, there is no units here. I didn't say 1 mile, said just a radius of 1. I didn't give you units, did I? So radians comes in when I don't know what units it is. That's why they get back out of the way when I do know what units it is. Okay, maybe. Some of you guys have just totally screw him. He's making this up as he goes. All right, they're on. So what about, here's the next step. So here's what we just figured out. If you don't understand me, there it is. S equals r theta. So now you can figure out any arc length. What's got to be true about the angle? It must be in radians. Okay. So what about the area of a piece of pie there? So if I have something like this here, well, let me put it more like over here. And here's the R. And I want to know what this area is. The cool thing is, let me take this out and put it like this. This is not a proof necessarily, but it's, the funny thing is, how tall is it? What's the height of this thing? R. Yeah, it's R, right? You with me so far? Okay, maybe. And what's the base? The base is curved, right? But still, how long is this?
S.
Which is
Theta R.
r theta. Now think back. What is the formula for the area of this triangle?
1/2 base times height.
Yeah, 1/2 base times height. Now the funny thing is, even though this is a curved bottom, the fact that it's curved makes this not the same length it would be if it wasn't curved. Are you semi with me here? So the really cool thing is they kind of average each other out. So the same formula applies. It's kind of cool. So what's the area of this? It's going to be 1/2 the base times the height. Right? R theta times R is R squared theta. It's a very cool, now that's not a proof. That's nowhere near a proof. But it is kind of cool that those play against each other, and it comes out to be exactly the same formula, really. The base is R theta, the height is R, same exact formula. Kicks ass. So if I want to know the area of what we call a sector, this is a sector of the circle, then we can use that formula there. Okay, so those are two little things they threw in: arc length and area of a sector of a circle. They threw those in just because we're talking about circles, probably. But just so you're ready when you see those. Just two little dinky formulas. They explained it a slightly different way than I just did. But they get the same formula, so who cares?
S just stands for arc length.
S is arc length, yeah. I know the letter S does not show up in either word, arc or length, but that's just too bad. So 6-1, this is actually where we're at right now. This is 6-1, specifically. So this is going to be your hell about this, is just remind me every now and again, I can tell you where we are. There will be a lot of bouncing around. Some of what we talked about today is in sections further down the road. It just is. So it's the only way I can do this. Everything kind of comes back on itself. It's almost difficult for me to go truly concept by concept. I have to do the whole thing and fill it in. But in section 6-1, there's going to be some conversions between radians and degrees. Oh, here's a neat one. If I have the angle, let's say, give it to you in degrees. If this is 320 degrees, what is this here?
40 degrees.
And to be more specific, do you see how 40 degrees is the reference angle, but it's not the real angle, is it? Because if I tell somebody, the one way that we can use angles and radius is to tell somebody, turn this much and then walk 5 meters out, right? So turn, let me do like this is the x-axis. Turn 20 degrees and then walk 5 meters out, I get to a certain point, don't I? Instead of X and Y, I can just say turn and walk. You with me? So X and Y is not the only way to get somewhere. So what's another way to get here then? Instead of turning all the way around 320, I can just turn back 40 degrees. So that's what a negative angle measure means. Instead of going this way, you just go that way. Right? Not a big deal. Just like a negative X means you don't go that way, you go that way. Same idea, except everything now is turned on itself. It's all a circle. All right, how are we doing so far? Another way to do this is to kind of screw with this person. If I made him do this, so what would that effectively be? If you start here and turn how far? How much more than 320 am I making him turn?
680 degrees.
I'm making him turn the full 360 extra, right? So I can do 320 plus 360, 680 degrees, and that's going to have him, he's going to end up at the same place. He's just going to be a little dizzy. You with me? Are you guys with me?
Yeah.
So this is what they mean by the words coterminal. Coterminal angle. How many angles can you tell? And actually, how many angles could you use here? A freaking infinite number, right? How did we get negative 40? 320 minus 360. Isn't that negative 40? Couldn't you subtract another 360 and another 360 and another 360 and another 360? Or add 360, add 360, add 360. You can get an infinite number of coterminal angles. The important thing is, it's called coterminal because if I do what they all say, I end up facing the same direction. So they all terminate at the same spot. They all have me facing the same direction at the end. How are we doing? So that's what the word coterminal means. They stop, terminate at the same place. Co. Maybe. You and my stats class have major poker faces. So like, if I did, what, Jeff? I don't know. 220 degrees. Give me one other name for that angle. One other coterminal angle. Yeah, so one easy way is to take 220 plus 360, 580 degrees. Let's make it turn another way. Somebody give me a negative.
140.
Negative 140. So that's 220 minus 360, negative 140. I mean, so that, the idea of coterminal, do not let it be difficult. It's not. Add several 360s or subtract several 360s. They all end up in the same place, of course, right? Maybe.
And 140? Oh. Okay.
Cool. Okay. Let's see. What else do we have here? Of course, they have just, here's a picture, find the arc length. So they're going to give you R, they're going to give you theta. Just remember, if they give you 180 degrees, you better make that into radians, because it has to be radians for this to work. That's it. Cool. No.
Go home.
That's it for section 6.1. Homework.
That's it?
You guys are really optimistic. I told you earlier we're going to be here the whole time. All right. So, I promised somebody, and I said this earlier, I want to make the connection between what the hell Sohcahtoa is and this way to do it. And I really, I know sometimes I speak my mind a bit much on mathematical concepts, but it's hard for a student to know how far something's going to take you. And trust me, Sohcahtoa will not take you as far as you need it to. But I'll show you what it is. So remind me, given this, what's the sine of theta officially defined to be? Y over h. And of course, we did earlier with the unit circle where the h was 1, but I don't care what I make it, it's always going to reduce to that same value. So it could be any h. It would just reduce to what it would be. be normally in a unit circle. Cosine theta?
X over H.
X over H. And we haven't done much with tangent today, but what's tangent theta?
Y over X.
Y over X. Careful, yes. So tangent theta is officially sine theta over cosine theta. Before I get into Sohcahtoa, let me just say this. Here's the complete picture. There are 6 trig functions total. And the other 3 are slightly lame, but they're useful. The other 3 are just the reciprocals of these. And here's how I remember them. S goes with C. Sine theta goes with cosecant theta. Let me say it like this. So cosecant theta is going to be H over Y. Right? So it's officially 1 over sine. So it's H over Y.
No. That's not inverse sine, right?
Not really. Is the inverse of sine, but it's not the inverse sine function.
Yeah.
So it's much better just to call it the reciprocal. Right? Because when you say inverse, this would be something most freaky that we're not to yet. Not crazy freaky, but still freakier than you think it might be at the moment. That is not what this is, right? Of course. A -1 on a function implies inverse function. This is just reciprocated, not the same thing. So cosecant goes with sine, secant goes with cosine. So I always just remember the C and the S are off. Right? Secant, which incredibly enough we call secant. This is going to be H over X. And the easiest one to remember, tangent. And everybody's got a co up here, don't they? Sine and cosine, cosecant and secant. So tangent better get his freaking co, or this ain't fair. So here's where cotangent comes into play. So that's the easiest one to remember. That's just going to be 1 over tangent. X over Y. Now, right now, you either feel bored because you're one of the few people that have done all this before, or you feel overwhelmed because it all seems like too much, right? And I don't know if anybody feels the third way possibility, which is this seems almost too easy. I don't think anybody's there. I don't know. But this is going right back to what I said. It should feel like to at least a couple of you guys that there's no way that this could be really extra useful, just making these stupid ratios of sides of a triangle. How the hell could that be useful for anything? If you really think about it, just make it look. That's all these are ratios of sides of a triangle. Ooh. So you might not understand yet how this is really useful, but we have immediate applications we could use this for once we start working with these things a little bit more. You get some classic problems like a ladder leaning up against a building, but yeah.
Why doesn't the cotangent have theta next to it?
Oh, it should. I just didn't want to write thing.
We'll just leave.
Pretty much.
We'll take 1 plus 1.
We'll take 1 plus. Extra.
All right. So you guys, so far so decent? So I added 3 more functions, but they're not really new. They're just reciprocals of what we already knew. And they are just ratios of sides of the triangle. So let me do this right now before I get into Sohcahtoa. Here's a problem. So that is a problem you should be able to do right now, no trouble. So do that.
Inverse, right?
Don't be giving stuff away now. But yes. So for those of you who hate radicals, I made you a nice one, right?
Yes.
Some of you guys might even know this, like 3, 4, 5 triangle. This is a 5, 12, 13. Currently enough, those are called Pythagorean triples. They're the nice ones. There's quite a few of them.
There's a 13 on that one, not the other one.
There is a 13 on both of them. I just moved the problem over here. So you can see it on there better. So this, either you know it or you don't from now on. Sine theta? 5 over 13. Sine likes y. And just to make the point here real clear, the angle has to be in the base. If I would have said this was the angle, I would have had to look at it like that. My x is here, my y is there. Because remember, what's it got to be in reference to? The angle has to be in reference to the x-axis. So if it's in the base, the x is where it's supposed to be. If I want it up here, I might as well redraw it turned around. Maybe. That's the only advantage Sohcahtoa has over this. And we'll get to Sohcahtoa right now here after we finish this. Cosine.
12 over 13.
12 over 13. No, I didn't say we're any quadrants. So these are actually, that's a good question though, it's a good point. But we're actually, you're thinking about like this. I just have a triangle sitting out there in space. Yeah. So this is a triangular shape of land maybe. I'm trying to figure out these trig functions. Because that's what people with land do all the time. Tangent theta?
5 over 12.
Yep, 5 over 12. All these are going to be easy now. 13 over 5. 13 over 12. 12 over 5. Woohoo. So here's Sohcahtoa. Sine of an angle is y over h. Y can also be seen as the side that's the opposite side, right? Opposite the angle. You guys with me? A little bit. Again, considering how I feel about Sohcahtoa, if you don't want to know this and you don't know this currently, you can take a break, look at the wall. I'm not going to require you to know this. I just wanted to let you guys know what this is. This is called the adjacent side because it's adjacent to the angle. And this, of course, can't call it anything else than good old hypotenuse. Or we spell it hypotenuse. So sine would then be opposite over hypotenuse. Cosine would be adjacent over hypotenuse. You with me? No, okay. Tangent would be opposite over adjacent. And so then they made this kid camp sounding thing. I went to camp Sohcahtoa. So you see opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Okay. Which is nice.
I didn't know the song, but I knew the poem.
There's a song?
No, the song, what do you call it when you do acronym?
Oh, okay. I got you.
But that's how they taught us in high school.
Gotcha.
But it was so
Now,
hard.
and I always want to be careful because I don't want you guys to think that I'm against easy ways to remember things. I am certainly not. I am against something like this is not going to take you as far as your math might need you to go. And this won't. The more you understand that sine goes like y, cosine goes like x, you're going to make it through physics more if you have to take any physics. You're going to make it through math more. And if you don't have to take any more, you can do this way for this class. What the hell?
How come it won't take it? Like when does it go away?
Because it's going to, for future problems, it'll make a lot more sense to think about cosine tells you the percentage that's in the x direction. Sine tells you the percentages of the y direction. That's really what it is. They are ratios, so they are percentages in those directions. So physics especially becomes a lot easier. Mathematical problems, applications towards physics, or just even math. Well, you don't know stuff yet. Well, some of the calculus stuff becomes a lot easier if I know what sine and cosine are based on. And Sohcahtoa doesn't really tell me the important stuff, the x and the y. Okay. We're actually to the point where we can do a real problem. Isn't that crazy? So here's somebody. And
I like the little small person.
and there's a tower or something here. I don't know.
Stratosphere, really?
What's
What's
that?
going to Vegas?
Yeah. Well, I was thinking about space a little. I don't know what I'm thinking about here. So there's kind of a tower here, and we know the tower is 500 feet tall. Let's say. You guys with me? A little bit.
Yeah.
I know the tower is 500 feet tall. Now, obviously, I've drawn it. Can you tell that there's no way for me to walk and see how far it is apart?
Sure.
Because otherwise, you know, there's alligators in it. It's that scene from Indiana Jones. The thing is falling down. Yes. I love that scene. All right, a few of you guys know what I'm talking about. Why is Indiana Jones? But I can measure the angle up to there. And I measure that angle is, I don't know, make something up, Jeff.
36 is kind of
No, I want something gross. Well, let's start with something nice, you're right. We'll make it 30. And then we'll do a problem where it's gross, so we actually have to use a calculator. This one you could do without the calculator. So if I do want to know how far away that is, I want to know how far away I am from the tower. I know the tower is 500 feet because I know this area, whatever. But I want to know how far away it really is. So I can see if I can jump. What can you set up? What trig function would relate what I know with what I want to know? And what I want to know is the x piece. See? Tangent. So the tangent of the angle is equal to what ratio? Yeah, y over x. 500 over x. Now, tangent is sine over cosine. And that's important because we don't really have everything memorized yet. Right? So what's the sine of 30 degrees? Yeah, sine likes y. 30 is far away from y, so it's going to be the smaller. It's going to be 1/2. Bless you. So the cosine of 30 must be the bigger dude. √3 over 2. You guys with me, sort of? So remember, you guys have to memorize these things. Not today, but very, very soon. You can probably imagine your first quiz on this stuff is going to have no calculators, and it's going to involve just filling in the blanks for... Why? What's wrong with people? Yeah.
Why with the half on the top? I thought you guys were the 3 over 2 on the top.
What is the sine of 30? So that's where we have to start. Because tangent is sine over cosine. Cool.
Yeah.
Sine of 30 is 1/2. Yeah. Because at 30, at 0 I have no y piece. At 30 I've got very little bit of y piece. So it should be the smaller value. And see, to me, that's the key thing. Sohcahtoa doesn't help you memorize things, but sine goes like y helps me memorize these values. Okay. Don't use each other too much. Or whatever you want. So here the 2's go away. So I get x equals, let me see if you guys can handle this. If you multiply this x up and multiply the √3 up, right? Just
Yeah.
solving for x. The 2's went away. Is that cool? The over 2's canceled.
866.
So now I just got to do 500 root 3.
866.0.
Oh, cool. Okay. So this will be 866 feet away.
You could jump that internet.
Oh yeah, totally. I pulled back. Don't worry. It doesn't make physical sense. This doesn't open very much, so this should be longer than this is tall. You with me? So it does make physical sense. And you see how this has got use. You ever see people out there surveying the land? They put that thing down, they look through the little thing, and they have somebody else, and they actually use like little laser pointers. And what they're measuring is the distance, and they also use the angle, and they see how much the ground has changed, how much it used to be elevated, and how much is not elevated anymore, to see if things are starting to sink or something bad. Yes, no, maybe so. Anybody ever work surveying at all?
I see him.
You see them out there? Okay.
See them out there.
They're using this. My little brother hates math. Lets me know about it every time I talk to him. And he went and shadowed a friend of his, seeing if he wanted to become a surveyor. And he called me. He says, "I understand TRIG now." He was angry because he's like, "Why don't they just make people work for surveyors? Then they'll know TRIG." I'm like, all right, good little James. Yeah. But I mean, it's a practical application. You start to see the importance of this stuff when you're actually out physical world. We gotta know if this damn thing's sinking so we can see if that building's gonna be okay. Then this stuff takes on importance. You're like, shit, I see how this works now because I can freaking see it. So this problem is my really feeble attempt to show you how this could help you in the real world. Yeah.
How'd you get x equal root 3 times 100?
Oh, just cross multiply. Right. Is that not good? So the over 2's cancel, so you get 1 over root 3 equals 500 over x. X equals root 3 times 500. Yeah. So that's going to happen often in trig because it's all ratios. So you're going to have to solve these. You're going to be cross multiplying a lot.
So, making sense. Never mind.
Is okay?
Yeah, I didn't. The 1/2. It's just I always think like trying to say it's the length, but it's not the length. That's just the ratios of the angle.
It is. Because this is if it was 1, and it's not 1. So, I mean, if you really start to look at this, the ratio 500 to x must be 1/2 to root 3 over 2 because this is a 30-degree angle.
Yeah.
That is what the angle is in lowest terms. Of course, I killed the 2's and I got 1 over root 3. And to tell you, honestly, I have never memorized tangent values. I just think, okay, if it's tangent of 30, I do exactly what we just did. You kind of with me? If you want to memorize tangent of 30, tangent of 45 is easy. 45 degrees is where they're both the same, so tangent of 45 is 1, because it's the ratio of sine to cosine. So tangent of 45 is 1, that's nice. And then it's either 1 over root 3 or root 3 over 1. But I've never really taken the time to memorize it. I just always kind of think sine over cosine. Let me try this again. When we looked at the unit circle and we saw that sine of 30 did equal 1/2, that meant that whatever length the triangle was that we're working with, whatever actually how big it was, the ratio of the sides would reduce to 1/2 no matter what. So in this case, tangent of 30 is 1 over root 3. Is that cool right there by itself? You guys with me? It's not a value we talked about too much earlier, but that's what sine of 30 over cosine 30 is. So tangent 30 is this. So that means the ratios of these sides must reduce to 1 over root 3. That's exactly what that formula says. This ratio must reduce to 1 over root 3. So if I solve it, I of course figure out what x must be for that to happen. If x ain't that, then this ain't 30. I measured that wrong somehow with my little angle measuring device. Maybe. All right. So I mean, if I have this 60, then what must the ratio of y to h here be? Let's call this h is fine. What must y to h be? What must that ratio reduce to? No 1/2. The sine, right? The sine of 60 is root 3 over 2.
Oh yeah.
It's y.
Yeah.
That's sine.
Yeah.
Maybe. Maybe not. All right. We'll try. So do you start to see what I was saying earlier? Some of you guys don't, I understand. But you will see. This is all freaking ratios. So on one level, it's nice to hear that, even if you don't quite believe me, trig is all about ratios of sides of triangles. So it can't be that crazy, terribly hard. At the same time, it should bother you. How could that possibly have that much significance then, if it's really just ratios of sides of triangles? Well, who cares? And I understand. I'd rather you get there. That's a good place to be. Then as we go through it, you start to go, oh, that's how this freaking has more importance. Okay. Here, you guys try this one. Oh, get your calculators out if you have them. I didn't bring any. So if you don't have them, just, it's okay. You guys see your sine, cosine, tangent?
Yeah. Yep.
So do this for me. Maybe I should put this on the overhead. Everybody got this here? Let me show you where some of this trig stuff is in your calculator. And then we'll try a harder problem out. So you guys see your sine, cosine, tangent? Now what's right above that? Those buttons. Those are the inverses, not the reciprocals. So do this for me. Do cosine 60. What should cosine 60 be?
0.5.
0.5. Now, how many of you guys are not getting 0.5? Don't freak out. That does not mean your calculator is defective or anything. So if you do cosine of 60 degrees, it should be 0.5. So let me show you how to switch it. If you didn't get 0.5, you're in radian mode, not degree mode. Yeah, like I was talking about earlier. Can you guys see this okay? Can everybody see this okay? That wants to see it? All right. So if I do cosine, let's see what this one's in. Cosine 60. Okay, so did you guys get that?
Yeah.
Some of you guys? Thank you. So if I go to mode, you can see right where it is. Go down to radians, now go to degrees, enter. So that's how you switch from radians to degrees. Under mode, yeah. Should be easy, right? You guys with me? So everybody that did not get 0.5, do this. Now go back. Second enter brings up the last thing I did. Now it's 0.5. Okay.
We want degrees, right?
Yeah, I gave it to you in degrees, so we have to have the calculator in degrees. If I said, what's the cosine of 1.89 radians, then you better go change it to radians. You guys with me? Mm-hmm. All right. So how would you get secant of 10 degrees? What's the definition of secant?
1 over cosine.
I love it. So the right way to do this is to do 1 divided by cosine 10 degrees. You can't use cosine inverse because that is the inverse function, not the reciprocal function, not the same thing.
Can you do the whole thing, x
Yes.
to negative 1?
Oh, sure. Yeah. So you could do this. 1 divided by cosine of 10. So here's the secant of 10. How we doing? Or like somebody just said, you could do cosine of 10. Get in there. The whole thing. There, right? Because that -1 means reciprocate. It's a -1 power, not a -1 meaning inverse function. You guys with me? A little bit? Yeah.
Which
How come
section
you
is
don't
that?
go straight
Like
up?
the secant of.
Oh, it's in a couple sections. It's in 6.2, and it's in 5. Oh, where are you at? 5.2.
6-2 on 5-2?
Yep.
Oh. 6-2 and 5.
Because I don't think they talk about in 5.1. No. Yeah, 6.2 and 5.2. How are you doing so far? Decent? All right, let me give you a word problem to try then.
Okay, can we do group?
Sort of a word problem.
We're doing a ladder thing.
You want to do a ladder thing?
No, I don't like
You don't like those? I don't like them either. It's kind of stupid. It's like, just go over and look at the ladder. So there's a problem. And a ladder laying against the building, and you see this all the damn time. What's more interesting is if the ladder starts to slip, and then you start talking about the velocities. That would be a little bit more interesting. But you just have a ladder laying against the building. You know the ladder's 11 feet tall. Well, then how far up the building is it? Who cares? So to make it more interesting, you could say there's a certain angle at which the ladder can be at. So, if it's too much up, it might tilt back or something. So then you could say the ladder is this long. How far up a building could you go safely with that ladder? That would be interesting. Because then if somebody's stuck on the 8th floor and you can only go up to the 7th floor, sorry. Go ahead. All right, well, let's do something different. Let's do. Now that one's neat. Now, oh, here it is. Perfect. So we have a. You want to do another tower problem? Here we go. Here's an airplane problem. So here's an airplane.
Really?
That's a little better. All right. Let me set this up here a little bit. Here's a car here. Oh yeah, you know my car's gonna be awesome.
Looks like a train.
Oh yeah, it looks like a little
What's
train.
on top of it? I'm
It's
very
on
confused.
top.
It's a Pope mobile. Alright. Let me work this out a little bit for you so make it easy. So there's a airplane is 5,150 feet above the highway right here. And then there's 2 cars in the highway.
Okay.
Oh yeah. And the angle from this car to the airplane is, where'd it go? 52 degrees, and the angle from this car to the airplane is 35 degrees. You guys got the basic idea?
Yeah.
5,150 feet. 5,150 feet, yeah. Not miles, I think that's big. Project X. We're up out in space. They're asking you how far apart are the cars on the highway? What is this distance here? Now the problem involves how many right triangles? 2. So I'm going to have to kind of piece this together. And on one level, does this make sense? Which car is further away from being right underneath the plane?
The one on the right?
Yeah, this guy. Because the further I go away, the shorter that angle gets. Does that make sense? If I'm here, now the angle is going to be, like that big. Now it's that big, and the closer I am, and of course if I was right underneath it, the angle would be 90. Right? Okay. Doing good. So this boils down to finding two lengths from the two triangles that I'm given. Both triangles share this side. So let's do one together. This side here, I'll mark it X. It's a really good idea. What ratio can I set up for this, and what trig function do I use?
The sine angle. Not cos tag.
So the one I know is this, and what is that? That's the,
Opposite.
all right, Sohcahtoa. That's the y. So what involves the ratios of y to x? Tangent, cool. So I can write the tangent of 52 must be what to what? Tangent of this angle has to be, yeah, y to x, 5150 over x. All right, now solve that. And you basically have the setup for the next one. You just have to use the right angle for the next one. So everybody should be in degree mode now, hopefully. Where'd it go? Angle 52. And a really good shortcut thing to know about math is I can just switch those, right? The x can multiply up, the tangent divides down. So I want to do 5150 divided by that number. So I can do 5150 divided by the answer, that number. So I don't have to write that whole damn number in again. How are we doing? The really nice thing about these is the formula is not difficult. The equation I end up with, very simple. And this is really nice, especially if it's a number I don't know, because then I have to use my calculator. Jeff can't yell at me for using my calculator because I have to figure out freaking 50 degrees, right? So no, I can't yell at you then. On the test, you better understand that I will give a couple where I will say, I want the answer in exact form, meaning no decimal. I want to see the root 3's and all that kind of business, which means I'll give you an angle that you should know, like 30 or 60 or 45 or whatever. You guys with me? So what do you guys get for that? Let's see. Yeah, 4023. So this is 4023 point, whatever it was, 62. And now this here, I'd solve it the same way, except instead of 52 degrees here, I'd have 35 degrees. They just happen to be the same triangle in a way. They both share the 5150, it's just that this side is longer or shorter. So they have the same ratio going on here, really. So tangent 35. So this other one, and just to make it all official, let's call it x1 and x2. Why not? So now I just got to do 5150 divided by tangent of 35. And I get 7354. Point whatever it is. 96. So now I just add those together to get the total distance apart.